Hi, everybody. So today I want to do something a little bit different. We're going to talk about not something great, but maybe the 10 worst things that I did in software. And so we're just going to go through kind of a quick overview of some of the things that I've done, and hopefully you can learn from this. Okay, so the first mistake I want to talk about, not always verifying new software versions. Assuming new versions will run the same or same products. Some products have a service that they can back check some of the results from a previous version. Most don't, though. Most of them you're going to have to do your own checking, and probably want to check multiple different scenarios. One of the worst examples of this is when I went to update to a new version. Love to be an early adopter. I love to go ahead and grab updates as soon as they're available, but crashing the model, and then the model, you can't get it back. So that is certainly one of the things that you want to be careful of. So maybe solution is going to be stop being an early adopter at least at a minimum. Maybe try it with a sample model and adopt once you have some confidence in the new version. Second mistake, looking at default settings as standards. They're not standards. News to everybody. They're just starting points, initial values at best. It's really better to start with nothing. You really want to go ahead and rethink every single value that's in a software program, never just using the default. So really, the only solution is going to be looking at everything that's in a software program as completely wrong or just a blank slate, and really kind of defining everything as you see fit. When we're building our models, building models that are too simple or too complicated are things that we definitely want to think about. I'm going to actually start with an economic model here to kind of show, kind of what I'm talking about. Really, when you build a software model, there is a point of diminishing returns. You want to start building a model, you're going to be adding more information, then you really want to kind of approach that point of maximum yield, kind of that top of the curve. You really want to kind of get there. But there also can be a negative, a downturn if you try to go too far with software modeling. So too simple is just going to be you're just building a little bit of information into the model, but you just don't have enough to work with. You're going to add some complexity, get better behavior, probably iterate to get a solution. But when I say you can go too far, I just mean you're probably adding members that really don't make a difference in the overall solution, and they can just make the model more complex. They can introduce new errors or potential problems within a model, and they're really not adding to the overall solution. So you can go too far with a software model. So just kind of to look at the curve a little bit closer. There's kind of just that data, and then you get a first model that runs without errors, and that's really kind of just an initial pass. Then you're going to provide more low definition, better member definitions. You're going to refine the model, provide more member definitions, refine the model again, probably iterate this process a little bit till you approach that point of kind of maximum yield. And then, like I said, you just don't want to go beyond that. You really want to get to that maximum point. Not to be confused with this confidence knowledge curve. This is one for younger engineers. You really have to be careful of, because we really want to get to that actual peak. You don't want to get to some false peak because of ignorance. You really want to kind of push beyond and get a lot of knowledge, and make sure that you get to that expert level model. But this is certainly another curve that I think could help as we think about software models. And we just, like I said, you want to avoid that ignorant section. All right, so building models that are too simple or too complicated. So you don't simple of a model. You don't want to ignore members that are important. You don't want to get too complicated either and add some of those unnecessary members. One of the other things you need to look at is it buildable. Take time to make sure the model and the drawings and the actual software model match. Any discrepancies between the model and the drawings are going to win. It doesn't really matter what's in the model if you don't have it drawn. Drawings are really going to be kind of your translator between the model that you have and the actual model that gets built in the field. You want to make sure that translator, that those drawings actually have all the information that you need. So a model can be meaningless unless it's connected through those drawings to the actual building. So again, the solution is going to be starting simple, adding in complexity. Keep adding in complexity till you get to that point of maximum yield, and then just remembering that drawings are going to be that connection. That's going to be your translator between your model, software model, and the actual structure. Using inappropriate model releases, over-released model, very few things are actually pin support. Something that is really important to remember. An over-connected model, fixing all ends of all members to get rid of local instability errors. And I see that probably being the more common mistake as you're trying to set up kind of a simple model and you start to get some errors. Hitting fix all is really going to solve some of those problems, but really in reality you can't have that much fixity. And then at the end of the day, do your drawn connections actually match your end release conditions? Really could almost do a whole session on this. So what's the difference between a pin base, fixed base? Does your detail for pin base actually have moment capacity? Things that you should be asking yourself. And just because you model it doesn't mean that they can build it. So really, you want to think about your end releases. They have a lot to do with the overall behavior of your designs. So you really want to start simple. Again, add some complexity where needed, and make sure that you're using the right results to understand behavior. Next thing I'm going to pick on is diaphragm types. Rigid diaphragms are just dangerous, period. They're very useful, but dangerous. Semi-rigid diaphragms can be a very good solution, but they add a lot of complexity. I think a lot of times if I was to look at a model and if I thought it was going to be rigid, maybe that's some of my initial passes, my initial analysis, and then I let that complexity or the more complex model, because semi-rigid diaphragms have many more plate elements, a lot more conditions that you have to consider from an analysis model, so it's just going to be something that we want to be careful of. So solution is, again, maybe comparing the diaphragm with a real situation. Again, that's always going to be a good idea. And then we just want to make sure that we include and incorporate any settings that are necessary for the semi-rigid diaphragm. On the flip side, flexible diaphragms are also just as dangerous, I think, just because the way that diaphragms distribute forces, there's going to be a real situation that isn't necessarily to one extreme of rigid or flexible. Flexible diaphragms are not necessarily conservative. If you have some semi-rigid behavior and a redistribution of forces means certain members are going to get more load than maybe what a flexible diaphragm would consider. So making sure that, again, thinking about our semi-rigid diaphragms, thinking about some potential issues, and making sure that you have a valid diaphragm for your design. Dynamic analysis, I have to bring this up. Again, we could do many sessions on dynamic analyses. We're not going to include all of that here, but some of the simple things that people do wrong, not including enough mass or stiffness. Obviously, those are going to be your key elements for a dynamic analysis. You could have isolated areas, so the primary period in the X or Y direction could be based on some isolated area. So we want to make sure that we're including enough of the overall structure to get those primary dynamic results. Including too much without proper inclusion into the model, assumptions that you make are not always going to be conservative. You want to be accurate, and so there's oftentimes where I see people making some assumptions about certain values of different members, and that's not conservative. Even if you pick low strengths or high strengths, the more accurate is going to be the more conservative. So dynamic analysis, I really look at it as it should be more like an academic project. It really should be quite a bit of work that gets put into it if you're going to consider any sort of results. Because I just do think it's unlikely that a simple dynamic analysis for a complex building is going to be useful. Really, put in the necessary time or use historical approximations is really going to be my suggestions for dynamic analysis. Next mistake, all model loads do not make it into the real foundations. You have to really do kind of make a check of the loads that you model that you think are getting put into the model. Do they end up actually at the reactions at locations that you have foundations? Because do you have residual reactions? Do you have what I would call sky hooks? Do you have some node or some place within the model that you have defined as a support that's not really support? You have to make sure that you looking at that. Do load generators work? Are they looking at and picking up all the load that you have modeled? Do you have all of the right factors on the right load cases? So all of the loads are getting through the model the way that you think they should be. So really kind of equilibrium checking is going to be important. Order of magnitude, kind of reality check. You really should be able to understand what some of the loads are. This is going to be for both gravity loads and lateral loads, and certainly if you lose any load generators, are they really giving you the actual load that you want to have in a model? Residual forces in members, we talked about residual reactions. Residual forces are really going to be, those analysis results that are within models. We do a really good job of defining a model. We do a great analysis. The software is doing a really good work in crunching a bunch of numbers. And then there's going to be certain results for members that are going to be checked by the program. And what I would call residual forces are going to be the results in members. Maybe it's weak axis bending. Maybe it's for members or connections. Maybe it's a torsional force that gets collected for a member or a plate element. Do we have a check on those members, or do we not? And do we have a good way to make sure that any of those residual forces are within capacities or they're not substantial? Really, there's not going to be a really good way to do that other than some sort of a manual check or some sort of a program check that gives you some of those. Because again, for finite element analysis, we have this pre-process modeling. We define this model. We get all the different types of stuff in here. We get to this solving of the analysis, and that's a really great step. That's mostly done by your software. You're going to define some criteria in here, but that's really going to be kind of a software-driven step for FEAs. It's really going to be this step 3 where we're going to review some results and design. So you can't skip one. You can't just go from a modeling to analysis to design. You really have to review those results, look for those residual forces, make sure that your results are what you would expect. You're doing some back checking, and then you can move on to that design step. So another mistake that I've made is assuming software is always right. Again, programming is can potentially be doing something that it's not. I've made this mistake certainly 100 times is probably a low number. Usually too busy, working too fast. You really do have to back check and make sure that you verify the software. There's going to be errors. We're all human. We definitely are going to be responsible. We engineers are responsible for our designs, and we have to be responsible for the tools that we use. And software is just that. It's just a tool. So we have to verify before we gain confidence in our designs. Just another kind of lens on this, you're going to have software used by engineers, sometimes usually in the 5,000 to 10,000 user range. And I always like to compare this to the smartphones, which also have errors, right? And they have billions of users, so they have a lot of people kind of back checking. And I would say that there's just really no way that a software program with a much smaller sample size of 5,000 to 10,000 is going to be able to catch all of these errors every time. So realize errors happen. Let developers know. They're certainly going to be interested in that feedback. I just had a really good example of a student looking at a software program and really working with the developers to fix an error that they had in there. And it's a great story. But it's definitely stuff that we have within analysis programs. We just have to work to let those developers know that so that other users don't run into those same problems. One of the other things that I like to then point out is that, software can't teach us. If we're looking at software programs, we really should have a really good understanding for, what design should be occurring. Software should make you more efficient. It certainly should speed up the process. It maybe is going to give you some insights, but it can't teach you. And so making sure that we remember that, and all of the professors that maybe see this will definitely agree with me. Software can't teach us, but it certainly can make us more efficient at our jobs, and that's the important step. But then I'm going to regress here just at the end, and because software can give us a better understanding of an overall software model. If you have a good software model, complex calculations can help you rethink some of your assumptions, because you're going to try to anticipate what some of the results might be. And I just had this example a couple months ago while I was looking at some results in that it wasn't, my intuition was telling me, something was wrong. And I kept looking at the model. Model was good, and everything that I've defined was good. So I think, looking at a deflected shape can really help us understand things. But I think the solution in this case is really keeping an open mind. If you do model everything correctly and the analysis is correct, and you're confident that there's no errors in the program, software models can give us new insights into how an analysis, especially with all the complexities that we have in software models, from just smaller buildings to larger buildings. Software can certainly help us have better understandings of how a building's going to respond to different loads. So one of the important parts of kind of back checking and doing some of this stuff is having a software expert, somebody that within an office, and maybe it's an external office, can go ahead and look for some of these designs, look at the designs and make sure everything is going to be working, maybe testing those new versions, benchmarking, looking at doing QC reviews. And honestly, the faster the schedule, the more I need software model peer reviews. I often hear about peer reviews that happen. A lot of times they happen for drawings. I want to encourage that even go deeper into the actual software models that are used to create the drawings. So develop a somewhat of a software expert program. Again, this could be internal, external, and it's just going to be somebody that's going to be able to help maybe people learn how to use the tools, but then also looking at some of the capabilities, limitations, and then looking at kind of doing those QC reviews for your project. So again, just to recap the session today, really we're kind of looking at building these models. We're looking at having better definitions and getting to that point of maximum return. Again, we want to start simple. We want to understand behavior. We're going to add in reasonable complexity as the project progresses. We don't want to go past that point of maximum return. We want to investigate, look for some unexpected behaviors as we add in some of that complexity. Have a process for quality. Make sure that we are more right. We know that we're getting better and better as we build the model, because it's really important to get to that final solution. We certainly want to make sure that we're building good, safe, reliable buildings, and never stop learning to be better engineers with software. I mean, they're great tools. They certainly can help us so much in our overall designs, and I just want to encourage everybody to be a continuous learner, keep using these tools appropriately, and keep advancing our profession. So with that, I just want to thank everybody for attending today, and I wanted to thank you for your time, and I look forward to the next time I get to talk to you.